Can you please repeat what you said?
So, I have told that start the recording. We have already started.
Sorry, I think your connection is not good or your mic is not good. I'm not able to hear you. What you can do is you can type your question in the chat and then I will look at it at the end of the class. Is that okay, Shipra? Okay, so then let me get any questions. Okay, then let me start with the next class. So general class notebook, and you are able to access all the material, right?
Yes, sir.
Good. Okay, let's get started then. So I will share the screen. Okay, so I'm actually putting these notes, these notes are all together. So this is today's class. Why? How do I get rid of this? So last time my sort of writing got spoiled. I was wondering if I should write here on the Teams app or on the browser. That is what I was actually trying. Let me just continue with writing here, and I'm hoping that today it will be better. Okay, let's get started. Okay. Okay. So now last time so we are done with the concept of specific intensity and sort of things related to it. Today we are going to start with the radiative transfer equation, which is sort of the main equation for the macroscopic treatment of radiation interacting with matter. Okay, so let's get started. So at the end of the last class, I showed that specific intensity, I knew, is a constant along the path of a ray. Okay, along the path of ray bundle, and there is sort of like a reciprocity between the source and the source and the emitter, which is the source, and observer, where you're observing the radiation, or there is a reciprocity between the solid angle and the area through which the photons are crossing. Okay, so let's go. So I'm actually trying to use a thinner pencil that may help. Okay, so in the radiative transfer, in absence of any material, photons just go unabsorbed, or there is no more photons added in the path of the ray. But if you have matter, you can have, electrons getting accelerated, or electrons going from a high level to a low level emitting photons. So you can have emission. So let's just say, oops. No, just a second. No. I think I'm gonna use the other interface. This is not working nicely. Let me try on browser. After the last class, I actually tried it on browser, and there it was working better. Okay, let's see. Draw. There is sort of a lag which I am feeling. Oh, I'm sorry about this. Yeah. Okay, let me try. Okay, so let's see. So there are three different processes that are important for radiation interacting with matter. First is this is not working. Just a sec. Let me. Oh, man. So in the meantime, you can ask questions now, since I'm trying to fix this, get this thing fixed. My writing thing is not working fine. So while I try to fix it, will you you can try to ask me some questions. Okay. Oh, just give me a minute. I think what's happening is there is a lag. I'm typing, but I'm writing, but it takes a lot of time for it to get reflected on the screen. So let me try. Hopefully situation will not get worse. So there's emission, there is absorption. No, this is not good. Okay, let me actually just close it and open it again. Just give me a sec. Hello. You can hear me now, right?
Yes, sir.
Okay.
Yes, sir.
Let me try again.
Sir, it was okay in the last class. We could, understand it, whatever you were typing.
Yeah, I mean, but if there is a lag, no, I cannot understand what I'm writing. There's a little. I mean, suddenly at the end of the last class and today, right at the beginning, there was great deterioration in terms of the lag, and that is actually not good. I mean, it basically, yeah, means that I have to again keep trying on finding something which works better. So let me say, so emission, absorption, and scattering. See, I cannot. So there is emission, absorption, and scattering. These are the ways in which radiation can interact with matter. So what I'll actually do is, rather than writing too much, what I'll do is I'll share this book, which I have the PDF of, and I will actually annotate on the book. I don't think this is actually working. So let me get that book, and since I'm actually closely following the book, I can.
I think it may get into copyright issues or not.
It's fine. Don't bother about that. This book will be available through library legally very soon. So don't bother about copyright issues. Let's focus on learning. Okay, so you can see the book?
Yes, sir. Yes, sir.
Okay, so let me just sort of go over the material that I was planning to go over. So this all we have done. Okay, so if a ray passes through matter, energy can be added or subtracted from it. This addition of energy is through a process called emission, and subtraction of energy from it is through absorption. And because of these processes, the specific intensity will not remain constant, right? So there is also a process of scattering in which photons come in and out of the beam of the radiation. So let me actually do one more thing. Whiteboard. No. So what I was trying to do is to get the whiteboard open as well. So if I have to, okay, here we go. Okay. Not this one. Okay. Oops. My goodness, this is very sensitive. Okay, so I will try and see if the whiteboard works better. Let me try. Oh my God, this is much better. Okay, so I think I'm gonna use it. That thing became slow. Maybe it became slow because I have so much material on a single page. That may be the reason. You know, I'm just adding to the same notebook, the same material. Anyway, let's see. Okay. Okay. So I will start here. Okay. So this is, yeah, this is much better actually. Emission, absorption, and scattering. Okay, so these are the processes through which the specific intensity changes along a ray. So today's date is 14th October. So this is today's class. So this was the whiteboard that I created when I write something on in our Friday session, or something that I write and share, but I'll perhaps also teach using this. Okay. Okay, so if you have like you know, if you're considering a beam, and so there is a specific intensity along this beam, and this independent variable is path length along the beam, which is represented by S. So if you have emitting particles, emitting matter along the path, right? So we define something called an emission coefficient J nu. Okay, so this is the emission coefficient J nu. What is meant by J nu? dE is equal to J nu dV dt d omega d nu. So basically, this is the amount of energy in photons added because of emission, due to emission created by this matter, which is emitting photons in volume dV. So if this length is like ds and ds, and this is the cross-sectional area is dA, so dV is nothing but dA times ds. This is time dt. This is the time over which the photons are added by emission. G omega is the angle, the solid angle through which these photons are passing, and d nu is the frequency range. So J nu, so this is energy. So the units of J nu are erg per centimeter cube per second per steradian per hertz. Right, so this is emission coefficient. If you have an, if you have an isotropic emitter, then J nu is nothing but P nu by 4 pi. Basically, P nu is the power emitted along all solid angles. So per solid angle, it's just P nu by 4 pi. So this is power. Emitted in all directions. Okay. We can also define something called emissivity. Emissivity. See, as I said, a lot of these things are about depth.
Sir,
Yeah.
this is Kinjal. I think it will be power emitted per unit volume.
Yes. You know, see this one, right? That is correct. It's emitted per unit volume because I have only integrated over solid angle. So you know the units of this and this only differ by per steradian. Per steradian. That's correct. Yeah. That's fine. So we can also define emissivity which is energy emitted per frequency per time per unit mass. So all you do is epsilon nu. This is emissivity. This is equal to J nu times rho. So J nu is per unit volume, and rho, the matter density, is mass per unit volume. So sorry, J nu divided by rho, not multiplied. Right, so J nu is emission per unit volume and all these other per units. So J nu divided by rho becomes emission per unit mass of the matter. And in fact, so this is also sometimes, you have to just be careful about the units. This is sometimes defined as integrated over all solid angles. But that's, all these are trivial things. Just be careful about the units when these different quantities are used. Okay, so sometimes you have this 4 pi here. So if you have 4 pi J nu, that's just like P nu divided by rho. Okay. So what about if you have, if you consider a small section of size ds here, and if you have beam intensity I nu coming here, what would be the intensity which leaves this small length, right? So this change in specific intensity, if you have emission in the medium, is equal to J nu times ds. Right, so J nu is energy crossing per unit volume per unit time. So these time, solid angle, and frequency are all there in I nu, right? But I nu is per unit area, right? So per unit volume multiplied by the length is per unit area. So this is how specific intensity changes if the beam passes through a medium which is emitting. Okay, so this is how specific intensity changes. Okay, so this is about emission. What about absorption? So in case of absorption, so we define something called absorption coefficient. Absorption coefficient, alpha nu. Okay, and the units of absorption coefficient are in per centimeter. So this, alpha nu quantifies the loss of energy along a beam due to matter which is absorbing radiation, right? Matter can both emit and absorb radiation. So interaction of matter and radiation can give rise to both emission and just a sec. Okay. No. Okay, so absorption. So this is loss of energy in photons due to absorption due to matter along the line of the beam. So d I nu is equal to minus alpha nu I nu ds, right? So you can actually see, right, if again, if you consider this path ds along the beam, there are atoms or molecules or absorbers along the path. So the photon energy can be absorbed by matter along the path length, and that's quantified by this absorption coefficient. Okay, so if you have absorbing particles which have a number density n, so density, this is number density of absorbers, then the number of absorbers in this section, this n, is equal to density times the volume, which is nothing but this, right? So this is the number of absorbers. Now, the amount of energy taken out of the beam, energy taken out due to absorption, is equal to right, that's just minus d I know. This is change in specific intensity times area times solid angle times time and times frequency range. This is equal to I nu times the number of absorbers times the number of absorbers, so which is n ds dA. This is the number of absorbers along the line of sight. Sigma nu. This is the absorption cross-section. Absorption cross-section, which has units of centimeter square. It's an area, it's cross-section, times d omega dt d nu. Right, so this is the energy, this is the energy taken out. So this is the expression in terms of the absorber properties, like cross-section, and this is just the definition of how specific intensity changes. So just by equating these two, we get d I nu equals minus n sigma nu d n sigma nu I nu ds. So this is how specific intensity changes because of absorption along the line of sight. Okay, and you can actually see by comparing with this expression that alpha nu is nothing but n sigma. So alpha nu equals n sigma nu. Right, n is the number density of absorbers, so it's centimeter cube, and sigma is cross section, which is centimeter square. So alpha nu is per centimeter. So this is how much energy is absorbed per unit length along the beam. So alpha nu also has a interpretation in terms of the mean free path. So we know that the mean free path is equal to 1 by n sigma. So if sigma is a cross section, mean free path is sort of defined like this. So if you have, if you consider like a, can you please mute yourself? Someone has a mic. Oh, someone has a mic which is not off. Hello, Harsh Raj. Okay. Anyway, I'm having tough time navigating all this. Don't add to the problems. Okay. So mean free path. So are you all familiar with what is the mean free path? So there are these scatterers with each particle having some cross section sigma nu in this case. Now mean free path means like what is the typical distance over which a photon, which is sort of, or a particle or a photon that's shown on this medium will get absorbed, right? So you can actually think of sigma v as the area, cross-section area of all these particles, right? So basically the length over which these areas, the projected areas, add up to unity is what mean free path is. So sigma v times these have some number density. So just a sec. So the number density times the area of an individual particle times the mean free path is equal to 1. This is how you sort of define the mean free path. That over this length, you will, this incident photon will encounter one of these particles. And this is like a standard definition, which should be familiar to a lot of you just from kinetic theory or thermodynamics. So the difference here is just that it's the photon interacting with atoms and molecules rather than a test particle interacting with particles, right? So you must have done this in the context of collisions between molecules in air, right? In that case, the cross-section is just the size of the molecule. In this case, this cross-section is determined by the physics of interaction between matter and radiation. But this concept of mean free path still holds. Okay. The other thing is we can actually define the collision frequency. Collision frequency of photons with particles is nothing but n sigma c. You can see this n sigma has dimensions of 1 by centimeter. C is speed of light, so centimeter per second. So this is per second. How many collisions do photons have with matter per second? And you can actually see that if the density is high, density of scatterers or absorbers is high, the mean free path is small. If the cross section of each of these particles is high, the mean free path is small and the collision frequency is high. So this all makes intuitive sense. Sometimes people also talk about something called mass absorption coefficient or opacity coefficient, which is defined as kappa nu, right? So this is basically kappa nu is equal to alpha nu by rho. So which has units of centimeter squares per gram, right? Because alpha nu is per centimeter and rho is grams per centimeter cube. So basically this quantifies how much is the absorbing power per unit mass for the medium, this kappa, which is called mass absorption coefficient or opacity coefficient. Opacity coefficient. Right. So let me just give you some sense of what the typical values are. For example, for Thomson scattering, I mean, this is scattering that I'm talking about, not absorption. There is a difference between scattering and absorption, but we know that, I mean, the cross section for Thomson scattering is 10 to the 6 times 10 to the minus 25 centimeter square. right? So kappa due to Thomson scattering is right. So this you can actually you can write this in terms of sigma, right? So alpha nu is nothing but n sigma by rho, which is equal to sigma divided by mass of the particle. And let's assume that these are all protons. So the kappa for Thomson scattering will be 6 times 10 to the minus 25 divided by the proton mass, which is 1.7 times 10 to the minus 24. This is about unit, about 0.8. And we can just make it 1. This is about 0.6 centimeter square per gram. This is useful to know. Now you notice that this cross section is much smaller than the cross section for the collision of particles, right? For example, if you have a molecule, right, say a oxygen gas or something, and then the molecules have a size of 1 angstrom, right? That's the typical size of atoms and molecules. I'm not being very quantitative here, right? So the cross section for this is just the size squared. So that's like 10 to the minus 8 squared, 10 to the minus 8 centimeter. One angstrom is 10 to the minus 8 centimeter. This is like 10 to the minus 16 centimeter square. You can actually see that the cross section for interaction of matter and radiation is much smaller. I'm mentioning Thomson scattering, but this is sort of overall scaling of matter photon interaction, whereas this is like orders of magnitude higher. So what it means is that collisions are much more common between molecules among themselves rather than with radiation. So for example, light that comes from the sun, right, through the atmosphere does not interact much with the atmosphere, but the particles in the atmosphere, the gas molecules, are interacting much more. So it's just useful to know these order of magnitude cross sections. Okay. Now, so this sort of picture assumes that this picture where this mean free path can be written as 1 by n sigma assumes that the size of the particle, or the effective size of the particle, which is just this, is bigger than the mean distance between the particles, which is just n to the minus 1/3, right? So if n is the number density of particles, n to the minus 1/3 is the mean distance between the particles, right? Because if you have if n is the number density, right, so this mean distance is nothing but n to the minus 1/3. Right? So this is one assumption, but basically that means that the size of these particles is smaller than the interparticle distance. Okay, if that was not the case, then this picture of mean free path will break down. Okay. And the other assumption that this picture makes is that the collision between photons and these particles are independent, right? So the fact that this photon is absorbed by this molecule or some other molecule, these are independent events. Anyway, these are the standard assumptions that we make in kinetic theory. So this is nothing very special. And you should recall that alpha nu is positive for absorption, but later we will see that stimulated emission, right? There are two kinds of emission according to Einstein's theory of radiation, interaction of radiation matter. One is spontaneous emission, the other is stimulated emission. and the intensity of stimulated emission is proportional to the intensity of the light itself. So that's why this is actually similar to absorption. So for stimulated emission, alpha nu is less than 0. So along the beam, photons can actually, your intensity can increase because of stimulated emission. So this will actually come back to later, but I just wanted to mention it here. So now we are in position to derive the radiative transfer equation. So what is the radiative transfer equation? So this describes how the specific intensity varies along the path if there is emission and absorption along the path. No. So I wanted to create some space.
Sir, I have a question.
Yes, please go ahead.
Sir, why do we need the interparticular distance to be small with respect to the, scattering cross-section, or root of the scattering cross-section?
It's -1. Yes, right. So basically, what this boils down to is the fact that the size of the particles is smaller than mean particle distance. Just a second. Okay. Let me actually. Yes.
Okay.
So
Okay.
what it means is that, the particles are not like this, right? In this case, particles have size. And so this is the mean particle distance and this is the size. And size in the sense of size that it offers to radiation, right? Cross-section is like an effective size, projected area. So this is not, we are not in this situation. We are in a situation where particles are like separated, right? And we want this situation because in this case, we can actually assume them to be like independent scatterers, right? Otherwise, if they are all like very, very close to each other, the cross section does not just add, right? The cross section of these situation 2, we can just add the area of this and this for the interaction. In this first situation, we cannot just add the area of this and this, right? Because the area is smaller, because there is overlap. So this is the reason. But this is almost always true. The gases and matter that we are talking about are so dilute. And the other thing, when I mentioned these numbers, I showed you that the scattering cross section is actually quite small, right? This 10 to the minus 25. So if you convert this as a size, so if you take a square root of this, so 10 to the minus 12 centimeter, right? 10 to the minus 12 centimeter is actually indeed very, very small compared to the mean particle distance. Okay.
Thank you.
Okay, so radiative transfer equation. So if we put both these elements together, d I nu ds, how does the intensity vary? This is equal to minus alpha nu I nu. This is due to absorption plus J nu. So this is your radiative transfer equation along the beam. And these are macroscopic coefficients, okay, as I already mentioned. These actually can be derived from the physics of the microscopic emission process. For example, you can derive this for Bremsstrahlung, which is free emission. Right, so or some other emission mechanism like line emission, ionized plasma, you have bound free, all these emission processes, you can actually calculate these coefficients. Okay, but once you have these coefficients from your microscopic theory, you can use them in the radiative transfer equation. Okay. Here we have not included scattering. Okay, in this course we are really not going to do scattering much, but scattering is very, very important, and it's done a little bit in the book. So the scattering is different from absorption. So in scattering, you have a photon, it sort of interacts with a particle like an electron, and just it changes its direction. Okay, and a little bit of its energy if it is at high energy. So you have Thomson scattering in low energy. So Thomson scattering or Compton scattering. So Compton scattering is the high energy version of Thomson scattering, but in scattering there is no, photons are not killed, they are not absorbed by matter, they just change direction. So what happens is, if you consider a beam, and if it is a medium which is scattering, so this photon which is going along the beam can change direction and can go in some other solid angle, but you can have photons which were going in some other direction. Because of scattering, they can also come in the beam because of scattering. So what scattering is sort of distinct from absorption, because it makes this problem of radiation matter interaction non-local in the solid angle. So there is a coupling between beams going in this direction and in this direction, right? Because these guys can get scattered into the beam, and these guys can get scattered out of the beam to all the other beams, right? So scattering is a little harder to treat compared to absorption and emission, but the concept is this. And so this is the radiative transfer equation. As you can actually see, because of this coupling in the angular direction, this differential equation that I have in absence of scattering actually is an integral differential equation. So what that means is that you have, you have a differential term here, but you have a term which integrates over all these solid angles omega primes. Okay, so you have an integral on the right hand side which involves an integral over omega prime. So that's why it's an integral differential equation. It's sort of similar to Boltzmann equation, if some of you are familiar with that. The Boltzmann equation in general is also an integral differential equation. And as I mentioned previously, I nu is very closely related to the distribution function in mu space, and this radiative transfer equation is also very similar to the Boltzmann equation. Okay, so that's sort of an aside, but as I said, we will not deal with scattering very quantitatively. I will mention a few things about it, but we will not do scattering in the radiative transfer, mathematical aspects of radiative transfer. Okay, so let's just look at some simple solutions. So if you have emission, if you only have emission, then the I nu ds, this is equal to J nu, and we are assuming that J nu is known. So this is known. In general, J nu is a function of density, temperature, and so on. So these have to be solved self-consistently. So the radiative transfer problem is actually quite hard, because these also have to be evolved through hydrodynamics. But here we are assuming that J nu is known, okay, as a function of S, the path length along the beam. So if we want to solve it, how do we solve it? So I nu equals J nu ds. So we just integrate it along the beam. So I nu 0, I nu at a distance s. So this will give you I nu at a distance s equals I nu naught. So this is the intensity space. So you have this sort of a geometry. So this is S equals to 0 and this is S. And you have some beam, you have some photons coming in this beam. They have specific intensity I nu naught at S equal to 0. And because of emitting matter here, right, which is emitting photons in this direction, J nu has that directional information, right? If it is isotropic, then you divide by 4 pi, so it only takes care of this solid angle. So I nu times integral J nu S prime ds prime 0 to S. Okay, so this is just a trivial integral, assuming that J nu S prime is given. That's normally not the case. Okay. So it's basically what it says is that the increase in brightness or increase in intensity is just equal to the emission coefficient integrated along the line of sight, right? This is what this is in words. Okay, so now if you have absorption only, in this case, dI nu ds equals minus alpha nu I nu, and this integral is also very easy. I nu S equals I nu naught e to the minus integral alpha nu S prime ds prime 0 to S, right? I mean, this is di by I will give you d log I, and this is minus alpha nu ds, which you just integrate. So the interpretation of this is that you have this medium, you have some specific intensity coming in. This medium only has absorbers, right? So, every small ds absorbs according to this. So you just integrate over all the absorptions happening along the line of sight. So, right, so specific intensity here gets attenuated by an exponential factor, which is, just the opacity of this medium, alpha nu ds of this part. Sorry, just a sec. So let me give you. Just a sec. So I spoke a little imprecisely. So what I'm saying is that here this material is not emitting, this is only absorbing. So and this thickness of this is nothing but alpha nu ds. So there is just an exponential suppression because of this factor. Okay. And this is actually, we'll come to this later, this is called optical depth. This is called optical depth, tau nu, alpha nu ds. So and this is dimensionless because alpha nu is per centimeter and ds is centimeter. So this is a dimensionless measure of a medium. So if for alpha tau nu greater than 1 is an optically thick medium, or an opaque medium, right? And tau nu less than 1 is transparent medium. A typical photon can cross a transparent medium, but not an optically thick or an opaque medium. So this is about absorption. This is all actually simple. So let's introduce this optical depth. Optical depth. So rather than and source function, these are some more. See, as you can notice, there are so many terms in this. There are so many terms in this course already, but they are actually rather simple. all you have to be attentive is about the units, so optical depth. So rather than using S as an independent variable in the radiative transfer equation, we can use something called an optical depth. So how is optical depth defined? So d tau nu equals alpha nu ds. This is the definition of optical depth, or what this gives you, tau nu equals integral of alpha nu s prime ds prime s naught to s. This is just integrated absorption coefficient along the line of sight, along the beam. Okay, if you have this, then our radiative transfer equation, which was di nu by ds equals minus alpha nu I nu due to absorption and due to emission. This equation, if you do a change of variable from s to tau nu, this equation becomes di nu. So you just divide it by alpha nu, so this becomes d tau nu equals minus I nu plus j nu divided by alpha nu, right? This ratio of emission coefficient and absorption coefficient is called source function. And most of the time, radiative transfer is done more in terms of S nu rather than alpha nu and J nu. And S nu also has a nice interpretation. So our radiative transfer equation becomes di nu by d tau nu plus I nu equals S nu. Again, we assume that S nu is given. Okay, that's not generally the case. So the radiative, this is only a formal solution. Actual solution of the radiative transfer equation involves, solving for S nu or J nu and alpha nu self-consistently, and that's much harder. So you have this equation. How do we solve this equation? This is a differential equation, right? Now we have both emission and absorption. How do we solve this equation? If you have an equation of this form, right, the standard way of solving it is through something called an integrating factor, right? If you've done a course on ODEs, that's what you do. So you multiply this by this whole thing by e to the tau nu, and the left hand side becomes dd tau nu e to the tau nu I nu, right? If you differentiate this, you get the left hand side is equal to e to the tau nu s nu. Okay, now s nu is a function of s, or you can also treat it as a function of tau nu. So if you solve it, you get e to the tau nu I nu at distance tau nu. Right, this is a perfect differential, so is equal to I nu at tau. Right, so these two terms are coming just from this. So what I'll do after this is I'll take this d tau nu on the right hand side and I'll integrate that, and if I integrate d of this thing, I just get these two terms, right? So plus integral e to the tau nu prime. So now tau nu prime is the integration variable. So s nu tau nu prime. We know s nu as a function of tau nu prime. D tau nu prime integral from 0 to tau nu. Okay, so this is the solution. This can actually be simplified further. So I nu tau nu equals I nu naught at 0 optical depth at e to the tau nu plus integral 0 to tau nu e to the minus tau nu minus tau nu prime s nu tau nu prime d tau nu prime. Is this clear? This is just simple mathematics. So let me actually show an interpretation of this. So you have some specific intensity I nu naught before the absorbing emitting medium. So this is a medium which is emitting and absorbing both, right? And in general, that's what happens. You know, matter absorbs and it also emits. So, so this I nu naught, this is sort of tau nu. This is the optical depth of the full medium, and we are sort of asking for what is I nu at tau nu. So the first term is nothing but this I nu naught is just exponentially attenuated, right? That's what we got. That's what we got here, right? This is nothing but that. The first term is nothing but this, right? So I nu naught e to the minus tau nu. That's e to the minus tau nu. This is the first term. The second term basically. The second term comes because of the emission from the medium. Okay, let's see then how we think about it. So now this, let's consider this small size ds or d tau nu prime. So this is d tau nu prime. This is the integration variable, right? So the material here will emit, you know, will add emission from this material will add to the intensity of the beam, right? But this is crossing through this medium, so this has an optical depth of tau nu minus tau nu prime, right? So you see this S nu added to the beam, S nu d tau nu, is attenuated by this factor, right? This factor e to the minus tau minus tau nu prime basically shows that this is the attenuation suffered by the radiation which is added by this small length. Okay, so the interpretation is actually quite easy. So all these small elements will add S nu d tau nu prime, but they will be attenuated because of the intervening absorption due to intervening medium. Okay, so this is any question on this? Good.
Oh, sir.
Yes.
Sir, here then the final expression shows that the absorption will be dominant over emission, because in both cases the part is attenuated.
Sure. Just a sec. In both cases?
In both cases, we are seeing that the intensity contribution term is getting attenuated. The first term is the initial intensity which is getting attenuated, and then the intensity coming due to the emission from the source function term that is getting attenuated.
Right. So that is correct, but source function is adding, right? It's not, you know.
Yes.
So you can have both addition of, right? You know, there is also addition of, so suppose I nu naught is 0. There is nothing coming from the inside this absorbing medium. Even then you can have something coming out because of emission. Although that emission is absorbed along the line, along the way, but still you can have intensity coming out, right? So there is both emission and absorption happening.
Yes, but that we are not getting the amount which we should get if there was no absorption. So
Sure,
that absorption part is dominating. Then I mean,
why do you call it dominating, right? You have both absorption and emission. Absorption will always happen, right? But S nu, because S nu is non-zero, there is also emission. In fact, well, let me actually simplify this a little more. Let's assume that S nu is equal to constant. Let's see. Let's assume that S nu equals constant. In this case, this solution becomes even easier. So I nu equals I nu naught e to the minus tau nu plus S nu times 1 minus e to the minus tau nu. You can actually see this, right? Because
Yes, sir.
so basically what it means is that, or you can also write it as S nu plus e to the minus tau nu I nu naught minus S nu, right? So,
Yes,
so you can actually see that as tau nu goes to infinity, as the medium becomes optically thick, I nu
yes,
approaches S nu, right? So this is actually the definition of source function, right? Source function is the
Yes, sir.
specific intensity attained by a beam, attained when the medium is optically thick. The medium which is emitting is optically thick, and of course, when tau nu is infinity, this background emission just just decays to zero, right? For example, if you have some very bright light source behind the sun, we won't see it, right? Because it's all
Yes, sir.
absorbed matter in the sun.
Yes, yes.
Okay, so right. So source function, the interpretation of source function is the quantity that specific intensity tries to approach for a large optical depths, right? Okay. Now we can actually look at a few limits. So when tau nu is much less than 1, so let's see. So tau nu is much less than 1. Yes.
But sir, sir, indirectly S nu is indirectly dependent on alpha. Means it's a ratio, means J nu by alpha.
Yeah. J nu by alpha. Right. S nu is actually that, but S nu is also this, right? In fact, J nu and alpha nu you have to determine from microscopic theory. But if I sort of give you just a medium and I tell you find its S nu, what you will do is you'll make like a thick an optically thick portion of that medium, and then just sort of see what the specific intensity that comes out. So it's very easy to measure S nu, unlike J nu and alpha nu. Right? All you have to do is just make it optically thick and measure how much intensity comes out.
So one more question. Optical thick means alpha nu is greater or distance is greater? I'm a bit confused.
No. Optical depth is this. This is absorption coefficient. Alpha nu is absorption coefficient. Tau nu is equal to integral alpha nu ds. So it takes both effects, right? If you have a long path length or very strong emission, you can have the same, both can give rise to a large optical depth. For example, if you are viewing through air, right, you can see through like large long distances, right? But if you're seeing through say curtain or something, you cannot see through a curtain. It's sort of thickish, it's optically thick. Or you cannot see through a wall, it's optically thick because its alpha nu is high, right? But for air or for whatever clouds, alpha nu is not that high, right? So the optical depth depends both on alpha nu and the length, right? So it's like alpha times L. So you can have a very optically absorbing medium with very thin, which is very thin. It can be opaque, or you can have like less absorbing material, but if you like assemble a very thick layer of it, it can be a good absorber. Okay, so optical depth has both the path length and the absorption property in it. So that's why tau nu is a better variable, because it sort of combines the two, and those two are more important than alpha nu individually in some sense. Okay, so for tau nu much less than 1, I nu is equal to I nu I nu naught, right? So if tau nu is small, then I nu naught just passes through. Plus, if tau nu is small, you can Taylor expand this, right, as 1 minus tau nu. So this will become tau nu S nu. So this is for optically thin, right? I nu is, so if you don't have any background light, then I nu goes like I nu S nu, and I nu is equal to S nu for optically thick medium, which is tau nu greater than 1, right? Right, so you can actually see here tau nu S nu, right? This is actually, we can actually write this in terms of J nu, which it should be, right? This is J nu ds, right? This is just, oops, this is just J nu ds, because tau nu is alpha nu ds. So tau nu S nu is just J nu. So this is J nu ds. So in an optically thin medium, you actually recover the same expression, but you can write it in terms of this. So, or in other words, if you make a graph of tau nu, I nu as a function of tau nu, for small tau nu, I nu is proportional to tau nu S nu. So it's linear with the slope tau nu, right? For large, it's sort of asymptotes, right? Right. This is how it looks like. This is how this function. This is how this function would look like. And this is just 1 minus e to the minus tau nu, right? So this becomes S nu for large tau nu, and it's proportional to tau nu for small tau nu. Okay. So there's also, just last thing in this class I will like to mention something called radiation force. Radiation force. Radiation force. So photons carry energy, they also carry momentum. So if the photons are absorbed by matter, they can transfer momentum to matter, right? So we can actually, because of this transfer of momentum, you can think about force exerted due to absorption of radiation. So I already mentioned this flux, radiation flux. This is nothing but I nu n hat d omega, right? This is radiation flux. So this is energy crossing per unit area, per unit time, per unit frequency. This is the flux. So if you have a surface, how much flux is crossing? And we also know that energy of a photon and the momentum of the photon are related like this, right? So we can actually calculate momentum absorbed per unit area, per unit time, and per unit length, ds. How much is that? That's nothing but, let me just write down. So this is the force. This is the force per unit volume. This is equal to 1 by c integral alpha nu f nu d nu. So this f nu is the flux. Alpha nu times f nu is, yeah, right. So this is per unit length. So that becomes alpha nu times F nu becomes energy absorbed per unit volume, per unit time, per unit frequency. Right? You now integrate over all frequencies and you divide by C to get the momentum. So this is momentum absorbed per unit area, per unit time, per unit length. And per unit area, per unit length is nothing but per unit volume. So this is momentum absorbed per unit volume per unit time, right? That's nothing. And momentum absorbed per unit time is nothing but the force exerted, right? Rate of change of momentum is force. So this is force per unit volume due to absorption of matter, due to absorption of radiation by matter. Okay, and we can also sort of talk about, so this is a vector, of course. We can also talk about force per unit mass. All you have to do is multiply this by mass per unit volume, right? So this is equal to 1 by C integral kappa nu F nu d nu, right? You recall this is mass absorption coefficient. So this is force per unit mass right, so momentum per unit time is force and this is force per unit mass. And if you recall, kappa nu was equal to rho. This kappa nu is centimeters, so kappa nu units are centimeter square per gram. So this is equal to alpha nu divided by rho. Right, rho is, so this is per centimeter, this is centimeter, this is grams per centimeter cube. So okay, so this is about the force, right? So emission, if the medium is emitting isotropically, emission does not cause change in momentum. So there is no force associated with emission if the emission is isotropic, right? But for absorption, since you are absorbing the incoming photons which are coming from a certain direction, there is momentum exchange or force exerted due to that. Okay, so this is this is it. So next time I will sort of start with thermal radiation and a little bit of black body radiation. I think all of you have done black body radiation to some extent. You can brush it up, and so we'll start with that. And also please do the homework problems. Okay, start doing the homework problems. That is also the material for our course, for our exam, right? Which the first exam will be end of this month. So it will keep you well prepared for that. Any question before I end?
Sir, this is Kinjal. So, I mean, I am having a problem that I am not being able to see this whiteboard.
Oh, you're not?
I think it's the same problem as streams.
Oh my God. So you are not, so but live you are able to see, but the same things you're not able to.
Yeah.
Okay.
Because like if you write in the Teams app, there is also a place for use the whiteboard in the class notes. There I can access, but
okay.
it in a different like in the
in this browser you cannot.
That we can't see.
Okay, what I'll do is I will try to copy
send the screenshot pictures. I mean that would.
Yes, I will do that. See, today somehow I was not able to use that class notes. I mean the writing was absolutely terrible. But then I switched to whiteboard and it was much better. So I'll figure it out. Don't worry. So let me see who else is in the class. It's very difficult for me to also monitor this aspect. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 people. Okay. So yeah, so also tell me, like, if something is not quite right, can I improve some aspect of presentation? This medium is not that easy. Teaching face to face is really much easier, and there are not so many unexpected issues like here. But here we just have to be a little patient. It's important if you have to read the textbook. Please do that. Please read the textbook continuously, otherwise it will be very difficult. Okay, so then
Sir,
yes.
do we have the class on Friday? I mean, I had a few things to discuss, so I mean.
Yeah, we have that evening, right?
Yeah.
We have interaction session. Yes, we will have that, right? Now homework is posted. So what I am thinking about that is that the TA, Ankit will start it. I will actually join somewhere in the middle. I don't want to join at the beginning, because then everyone asks. I have a tendency to answer and people ask me. It's also important that you guys interact with him as well. Okay, so I will actually join it, but maybe 20 minutes later. But that session is there every week, unless we state otherwise. Okay, so are the JAP students here? So Priyanka is here. Who else among the JAP students are here? Payal is here. Yeah. Okay, so people attending classes is important, but even more important than that is to actually read the textbook and the related materials. Okay, so I'll actually end the session. Sorry.
Sir, you should stop recording before.
Yes, yeah, I think. Thanks.
Yes, sir. Thank you, sir.